Okay, so now let's do a problem that's just slightly different, or that looks just slightly different. We're going to look at the problem epsilon y squared plus y equals 1. So instead of adding the epsilon, the small parameter epsilon, multiplying the y, we have it multiplying the y squared. And encouraged by the results we got from the previous problem, we're going to try a power series again in powers of epsilon as a solution to this problem. So we're going to look for a solution of the form y is equal to y naught plus epsilon y1 plus epsilon squared y2 plus dot dot dot. We'll substitute into the equation and collect terms, and then set the coefficients of each power of epsilon to be 0 separately. So plugging in, we get epsilon times y naught plus epsilon y1 plus epsilon squared y2 plus dot 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 squared plus y naught plus epsilon y1 plus epsilon squared y2 plus dot 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 minus 1 equals 0. Now we're going to rearrange the terms, collecting like powers of epsilon. So the first part we get, in this first term there are no terms involving epsilon to the power of 0. The first one appears in this second term, and we have y naught minus 1 times epsilon to the power of 0 plus. Now we're going to collect all the terms that are of power epsilon. In turn, we have just y naught squared, so we'll have y naught squared. In this one, we have plus y1 times epsilon to the power 1 plus. Now we collect the terms, the coefficients of y naught, of epsilon squared, sorry. And in the first term, we have the cross terms, right? That'll give us a term with factor of epsilon multiplied by this epsilon will be an epsilon squared. So there'll be 2 y naught y1 from the cross term in the first term. Then there will be plus y2 epsilon squared plus, and then we can keep going, equals 0. And as before, this equation, we want it to be correct for any value of y. So as y goes to 0, this term doesn't depend on epsilon, whereas these ones are all going to 0. So if that's going to be valid, then the first term has to go to 0. So that means y naught minus 1 is equal to 0, which means that y naught is equal to 1. From the second term, same thing. If this one is 0, this one is going to, as epsilon goes to 0, this term will vanish before this one. So we're left with this condition that y naught squared plus y1 is equal to 0, which means that y1 is also equal to, y1 is equal to minus 1 from this term. Then going to the next power of epsilon, epsilon squared, what we find is that 2 y naught y1 plus y2 is equal to 0, right? This coefficient has to go to 0. And that means that y2 is equal to minus 2 times 1 times minus 1, which is equal to 2. And we can keep going forever, get the epsilon cubed terms, and so on. The upshot, stopping after the first 3, is y is equal to 1 from y naught minus epsilon from this term plus 2 epsilon plus dot dot dot. Okay, so we're getting a solution, which is the solution where epsilon is 0, we just get y equals 1, but then we get the first, we got 2 squared here. We get the epsilon correction, then the epsilon squared correction, and we can keep going forever. So that looks good. Seems like the method is working, except that the original equation is a quadratic equation, and therefore we'd expect it to have 2 roots, but we found only 1, right? We only found the solution close to y equals 1, but there should be another one, and we didn't find it. So, and we can see why that is, because when epsilon is 0, this term vanishes and we just get the linear equation. So we want to see if we can develop a way of obtaining both roots for this problem. And the way we're going to find out what went wrong with this solution is we're going to use the fact that this happens to be a very easy problem where we know the exact solution, we know the quadratic formula. So we'll take the quadratic the solution from the quadratic formula, and expand that solution out in a power series, in a series in powers of epsilon, and see if we can learn what's going on, why we get only one root. Okay, so I'm going to keep this solution out here. So y is equal to 1 minus epsilon plus 2 epsilon squared plus dot dot dot. This is the solution we got so far. And now we're going to write down the solution in terms of the quadratic, from the quadratic formula. So that is y, whoops, this one is dead. Let's see if that blue one works. Y is equal to minus 1 plus or minus, this one's no good either, maybe the red. From the quadratic formula, we have y, yeah, that's a nice marker. Y is equal to minus 1 plus or minus the square root of 1 plus 4 epsilon all over 2 epsilon. And now let's expand this out. Oh, well, first, there's the two roots. Which one do we get? Which one is the plus? Which one is the minus? So let's take the limit as epsilon goes to 0 of this equation. So as epsilon goes to 0, what we get of y, we get minus 1 plus or minus 1 over 2 epsilon. And if we use the plus, then we get 0 over 0, right? And so, because epsilon is going to 0. So that means we have to use L'Hopital's rule with the plus. If we use the minus, then we get minus 2 over epsilon, and that one will blow up. So one of the roots goes to infinity as epsilon goes to 0, which is not that one. That's the one with the minus. So the solution with the minus goes to infinity as epsilon goes to 0. So that's the one we're missing so far. So this one here, y is equal to minus 1 minus square root of 1 plus 4 epsilon over 2 epsilon is the missing solution. Just to be sure that if I take the limit as epsilon goes to 0, I do get that. Let's try L'Hopital's rule. The limit as epsilon goes to 0 of this one, we take the derivative of the top and the derivative of the bottom. So from the top, we get 1/2 1 plus 4 epsilon to the minus 1/2 times 4, and on the bottom we get 2. And the limit as epsilon goes to 0 of that is equal to 1, right? Which is good because that's the root we get from here. So the solution with the plus is this one. The solution with the minus is something different that we didn't get from our regular perturbation expansion. So let's expand this one, see what it looks like. So this one, y is equal to minus 1 over 2 epsilon times 1 plus square root of 1 plus 4 epsilon. And then I'm going to expand this out in a Taylor series, or not in a series, yeah, in a Taylor series, I guess. This part here. So let's define f of epsilon to be equal to 1 plus the square root of 1 plus 4 epsilon. And f of 0 is going to be 2. F prime of epsilon is going to be 1/2 times 1 plus 4 epsilon to the minus 1/2 times 4. And that's equal to 2 times 1 plus 4 epsilon to the minus 1/2. And f primed of 0 is just equal to 2. And then f double primed of epsilon is equal to minus 1 plus 4 epsilon to the minus 3/2 times 4, so that f double primed of 0 is just equal to minus 4. And we can keep going. Now we could use these terms here to get the expansion of this one. So that means that f of epsilon is equal to 2 plus 2 plus 2 times epsilon plus 1 over 2 factorial times minus 4 minus 4 epsilon squared plus dot dot dot. So this is equal to 2 plus 2 epsilon minus 2 epsilon squared plus dot dot dot. Substituting this for this term in here, we get y is equal to minus 1 over 2 epsilon times 2 plus 2 epsilon minus 2 epsilon squared plus dot dot dot, which is minus 1 over epsilon minus 1 plus the 2 epsilon minus plus epsilon. So these are the first three terms plus dot 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 in the power series expansion of f of epsilon, of y. And what you see, which is very different than what we tried, is that the first term in the series expansion goes like 1 over epsilon instead of epsilon to some positive power, integer power. And so this means that there are some series approximations which may not have integral powers, positive integral powers of epsilon. So what we do in that case is we're going to try a more general form of the series expansion. And what we will do is try a solution of this form. So we try y is equal to y naught times epsilon to the power 8 plus y1 times epsilon to the power b plus y2 times epsilon to the power c plus and so on. And for this to be a well-ordered series, with each term getting progressively smaller, we'll want a to be smaller than b to be smaller than c to be smaller than so on, right? Because remember, epsilon is going to 0. And so if we ensure that a is less than b is less than c and so on, then this term in the limit where epsilon goes to 0, this will be bigger than this term, and this term will be bigger than the next one, which in turn will be bigger than the next one, and so on. Okay, now we're going to substitute this form of the solution into the equation. So what we end up with is y naught squared times epsilon to the 2a plus 1 plus, so I just squared the first one in the series. There will be some cross terms and more terms, but remember that this one is bigger than that one, which is bigger than that one. So the leading term in the first part of the equation will be this term. And then plus, and now we're going to do this one here. So the leading term will again be y naught epsilon to the power 8 plus the other terms minus 1 equals 0. And now we see, now what do we do next? Well, I guess there's different possibilities. It could be that these two terms are big compared to the minus 1, and these are the dominant balance. So these ones balance. Or it could be that these two balance, or it could be that the first and the last balance. And we don't know which one it is yet, so what we do is we do some casework. We assume each case in turn, and we see what we get. So let's look at case 1. Case 1, where this term and this term balance. So that means that y naught squared epsilon to the 2a plus 1 plus y naught epsilon to the a equals 0. And I guess that would mean either y naught is equal to 0, that's one possibility. But that's not a very interesting one, or even a possible one, because if we're getting a contradiction, because we assume that these two were the big terms, and that they were bigger than the minus 1. But if y naught is 0, then this is bigger than these two terms, and that cannot be the dominant balance. So this possibility, we can rule that out. Okay, so if y naught is not equal to 0, then what we have is y naught times epsilon to 2a plus 1 plus epsilon to the a is equal to 0. And if this is going to be true for any value of epsilon, then these powers of epsilon have to be equal, which means that 2a plus 1 is equal to a, or a is equal to minus 1. And if a is minus 1, then our solution, our leading order term, is going to be y naught times epsilon to the, oh, the epsilons go away, sorry, epsilon to the 0. No, is that right? No, times 1 over epsilon plus 1 over epsilon equals 0, which implies y naught is equal to minus 1. And so for this first term here, the solution, the leading term in the solution of y is going to be y is equal to minus 1 over epsilon, which you will recall, is the new root, the one that was missing from this one, right? We got this one start f1, the other one was close to, went off to epsilon going to infinity. Sorry, epsilon going to 0, leading y going to infinity. And so balancing these two first terms is going to give us the root that we missed from the regular perturbation. That was balancing these two terms, case 1. Case 2. Case 2, let's assume that the dominant balance is these two terms, right? Then in that case, we have y naught epsilon to the a minus 1 equals 0, which would mean that a is equal to 0, right? So if this is going to be a valid equation for all epsilons, this has to go, the a has to go to 0, so it becomes y naught equals 1, and that gives us y naught equals 1. And in that case, we get back, when we balance these two terms, we get back the original regular perturbation series that we just got from the previous analysis. But there's another case, there's the one that where the first term balances the last term. So we already found the series, the beginning of the perturbation series that will be equal to the two known roots of the quadratic equations. We might wonder, what about the third possibility where the first and the last term balance? Well, in that case, we get y naught squared epsilon to 2a plus 1 minus 1 is equal to 0, which would mean that 2a plus 1 is equal to 0, or a is equal to minus 1/2. And if a is minus 1/2, then the neglected term, this one, right, it's going to blow up as, right, as epsilon goes to 0. It'll be a term like y naught over the square root of epsilon. And as epsilon goes 0, this gets big, certainly much bigger than minus 1, and much bigger than the first term, because those two balances. And so we get a contradiction, right? We assume that these two were the dominant balance, but that's invalid if this term is bigger. So case 3 leads to a contradiction, and therefore it's not possible. So we do indeed get only two possibilities, and they are the ones where this balances that, which is the same solution as the regular perturbation, or where the first terms balance, which we get the other missing root to the quadratic equation. So this is an example of a method called the dominant balance method, where we write down the equation and we analyze case by case which one might be the leading balance to make the equation valid, and we can find out what are the possible cases and recover the missing root to this equation. All right, now we're going to switch over to a differential equation, which is where we want to apply this boundary layer method.